Hi, folks. Welcome to another episode of YFTT, Yugabyte Friday Tech Talks. This week is special. This week, we have with us Mikhail, one of our co-founders, who's been in the journey, right from day one. And, it's really, really awesome to be, really happy to be able to do this, bringing back a lot of nostalgic memories just being here with Mikhail. So thanks for joining us, Mikhail.
Thanks, Karthik.
Yeah, absolutely. We'll get started in a couple of minutes. Please stay tuned. Okay, meanwhile, maybe Mikhail, why don't you say a few words about yourself? Like most of the folks know you probably, but why don't you still just say a few? Oh, actually, we have a couple of minutes, so maybe we should just wait. We just chit chat for a few minutes until we go ahead. So, awesome. So I remember this was back in 2018 or 17 when you started working on DocDB. You proposed it. You were actually on vacation and you went and built most of the thing.
It wasn't in 2016.
16. Okay, it was even earlier. It was right in the beginning. Yeah, got it. Yeah. So it's been an interesting journey from there, huh? Like from building on top of RocksDB, coming all the way. So many, and all of the innovation that went in order to bring this all together. So
yeah, the term DocDB was initially just for the encoding of RocksDB keys and values, but then it grew to mean much more than that. The entire distributed storage subsystem of YugabyteDB is now called DocDB.
That's right, the transactional storage subsystem. Yeah, distributed transactional storage subsystem. Yeah.
Yes.
Fantastic. Awesome. Okay, so it's about time. So maybe let's get started. Once again, hi folks. Welcome to another episode of YFTT. This is a talk by engineers for engineers, and this week's guest is Mikhail, none other than Mikhail, one of our co-founders, and he's been the brains behind DocDB, which is the transactional distributed storage system underneath YugabyteDB. And as he was just saying, it was back in 2016. When he started figuring out what is the best way to use RocksDB for a transactional and relational database, and from there, he was on vacation when he started doing this. So what Mikhail does for fun. But anyways, let's just get started. Don't feel shy. Do ask us questions. You can drop your questions in the LinkedIn comment box. So and we'll get right back. So why don't we kick this off, Mikhail? Why don't you maybe very quickly introduce yourself? Most of the folks know you, but why don't you still introduce yourself really quickly, a few 30 seconds, and then we can get this show on the road.
Thanks, Karthik. So yeah, I'm Mikhail. I'm one of the co-founders of Yugabyte, and I worked with Kanan and Karthik back in 2011, 2012 at Facebook, and then I went off to work at another startup for 3.5 years, and then in 2016 we started Yugabyte, and it's been history since then.
Awesome. So, great. Yeah, let's get started. So DocDB, let's go right into it. First off, why the name? Why did we name it DocDB? Maybe you can just tell people that, and then
yeah. So initially we didn't know that we were going to build a SQL database. We were focusing more on the NoSQL, SQL and Redis compatible. That's a bit of history of YugabyteDB, and the generalization of those two data models is a key to a document, where a document could be either a row in more of a standard relational model, or it could be a data structure like a hash or a map or an array. So the name DocDB comes from a shortening of document DB. And since document DB was already widely used, I just shortened it to DocDB. So
all right.
So let's see where it fits in the overall structure of YugabyteDB. So YugabyteDB has a query layer which supports the two APIs, the SQL compatible and the Cassandra query language compatible APIs. And underneath there is the DocDB layer, the distributed transactional layer, which takes care of replicating each bit of data over the quorum using the Raft consensus protocol, and also supports distributed transactions. But one of the major parts that it does is that it supports the storage system on each node, and that is done using RocksDB. So we've decided to use RocksDB for storing the actual data, and we've done a number of enhancements that we'll talk about in this presentation. And the goals that we had when choosing the storage subsystem, we needed something, as I said, to support this key to document model. So we would have to store either a row or a data structure, and then this document abstraction, because we started with the Cassandra query language compatible model, and then around 2017 we became serious about adding full SQL support by using the Postgres code base. And so from the start it was also optimized for storing a row of a relational database, because SQL is also kind of relational. And we also from the start we had distributed transactions in mind. So there were already a few ways to implement a few designs for those distributed transaction systems in the literature. So that using one of those designs or building our own, which what we eventually did, was one of our goals. And pretty early we decided to use Postgres and to integrate Postgres as deeply as possible into YugabyteDB. So we needed a system that was flexible enough that would allow us to reuse native Postgres data types, and that's what we eventually did. So DocDB has some of its own data types, but for more complex Postgres data types like JSONB or arrays or any of the possible data types where Postgres takes care of the encoding and it would be too complex to re-implement it, we decided to reuse the Postgres encoding and just represent that as a byte strings in DocDB. But nevertheless, we also pushed down the code. We have the full Postgres backend code base available inside of our storage server process, so we could do query push down or predicate push down as close to storage as possible. So going back to this slide, it says RocksDB instance for tablet 1, RocksDB instance for tablet n. So I just wanted to say briefly what a tablet is in Yugabyte. Most of you are probably familiar with this concept, but a tablet is a shard that is replicated across a quorum of nodes. So it could be for a 10-node cluster, it could be some 3 nodes out of the 10. And so typically replication factor is 3 or 5, or it could be even larger, but 3 is by far the most common replication factor. And data is sharded in the tablets, and sometimes tablets could contain more than one table. So they could contain multiple tables, for example, for a collocated table for performance, because we don't want to incur the replication overhead for really small tables. And each tablet is backed by a separate RocksDB database. So it's a unit of replication, but it's also a unit of storage. So on all of the replicas, the tablet is represented by a RocksDB instance, or even 2 RocksDB instances, as we'll find out. But the primary one is the one that stores the majority of the data. So RocksDB is a log-structured merge tree storage engine, and we only write to it when we replicate data successfully using Raft. So, for example, when 2 of the 3 replicas replicate the data, one replica might be down, but that's normal in a distributed system, and usually it recovers quickly. But as soon as we do the consensus replication of a particular write operation, we write it to RocksDB, and in RocksDB, this write operation goes something like this. So it's a key value store. So the keys and values are byte sequences, and the keys are sorted. So it writes the key to value mapping to this mutable mem table data structure, and there could be one or more immutable mem tables at any point in time. So once this current mem table grows large enough to the configured value, it becomes immutable, and immutable mem tables are flushed to SST files. That's a sorted string table or a static string table file. That's a popular concept, I guess, popularized by Google Big Table paper initially. So immutable mem tables are written to these SST files, and on the read path we have to look for a particular key in all of these SST files, because it could be anywhere. And to keep the read path fast, RocksDB does, or any log structured merge tree storage engine does, so-called compaction operations in the background. So it takes some of these SST files and combines them into a larger SST file according to certain rules that we'll talk about. And this is how these systems operate, the LSM systems. So there is no random writes. All the writes are sequential. We write to files, and of course, for persistence, this assumes the existence of a write-ahead log somewhere. So RocksDB has its write-ahead log, but we don't use that. We use the raft log.
Yeah, and this was one of the reasons why we had to enhance RocksDB in the first place, right? Because writing to the raft log for distributed consistency, and then writing to the RocksDB log, and then writing to RocksDB was too much. So we had to take out the RocksDB log and change the way consistent MVCC, all of that stuff is done, correct?
Yes. So the way we avoid using RocksDB log is we every time we flush a file in an SS table file in RocksDB, we also record some metadata that says where what is the operation ID in the raft that this file contains data for. And when the server restarts, we read this metadata and we know where to start replaying the write-ahead log. So that allows us to avoid using the RocksDB built-in write-ahead log altogether. And RocksDB was already a widely used open source project when we were evaluating whether to use it as a storage engine for YugabyteDB. We were deeply familiar with it from Facebook, because we were working on HBase at Facebook, and at the same time another team was building RocksDB in C and C++, and they used some of the learnings that we discovered while working on HBase, like the compaction algorithm. The universal compaction algorithm in RocksDB is exactly what we did in HBase. And of course, using C and C++ as an implementation language allows us to avoid Java GC issues. So from the start, we've been building Yugabyte in C and C++, and that also allows integration with Postgres. And RocksDB was a good match. And also, RocksDB and log structured merge tree systems in general are good for SSDs. They're optimized for SSDs because SSDs work better with sequential writes compared to random writes. And there were, at the same time, there were a few things, there were a lot of things that we had to build on top of RocksDB in order for it to fit our needs as a storage system. So of course, it's just a library. It's an embeddable library, and it's used in browsers. I mean, like LevelDB, the predecessors of RocksDB, is used in Chromium or something like that. So and of course, RocksDB is widely used in server software, but all the server framework, all of that is built on top of it, or built next to it, and RocksDB only provides the storage system. And another consideration is why not use B trees, because a lot of databases use B trees, and some of the same concerns that I already mentioned, like sequential writes are better for SSGs, and while there are certain arguments why B3 random reads might be faster than LSM random reads, the write throughput can be solved by caching, and I mean, the read throughput can be solved by caching, and the write throughput is where the bottleneck frequently is when you add some caches. And also, LSM is even better for reader workloads if data is naturally time partitioned. Like, for example, if you're retrieving top messages in an inbox, those messages would be in the most recent SS table file in most cases if you're using an LSM storage system, and they would be cached, they would be easy to retrieve. So LSM was overall the best choice for the design of the storage subsystem. So let's go through how we, for example, store relational data. So this is the YSQL API, the SQL API. And let's say we have a table, a simple table with a primary key and a couple of data, a couple of value columns. And for simplicity, we'll split this into one tablet. So that's a custom YSQL syntax. We insert, let's say we insert a value. Let's say we insert a value, and we update this value. We update the column value to be different. And so first we insert an entire row with 2 columns specified, and then we update 1 column. So what we see here is that in the RocksDB we have this this encoding, and this shows the decoded format. So we don't store this string. We store the corresponding binary encoding of this, which is binary sortable, so that RocksDB can treat it as just opaque byte arrays. And we do automatic hashing. There is a way to turn it off, but in many cases for distributed SQL workloads, automatic hashing is useful to evenly spread the workload throughout the cluster. So in this case, the key is being hashed, and there is this hash value here, and then the actual value of the key as well. And then this is the MVCC timestamp, the hybrid timestamp that comes from the hybrid logical clock, and it is mapped to this initial row that we inserted, and it has column IDs for the first column and the second column. These are value columns like V1 and V2. All the key columns are stored in the actual RocksDB key. And then we overwrite one of the columns with a new value, and it is stored after this, but it has a higher timestamp. And at read time, we aggregate these two, and we find the actual value of the given column and the given timestamp. So, and the important part is that we're not overwriting the entire row here. We're just adding another record that says the new value of this column is now this. So this row might be massive. It might have 100 columns, and we're not overwriting all that data, unlike some other systems do. So when we delete, let's say we delete this entire row, then we just write a delete marker that repeats the row key and has a higher timestamp, and then it says delete this entire row. And then let's say we insert a new version of this row. Then this is a similar type of insert, this so-called packed row. So all the columns are packed into one RocksDB value. And later, when the compaction runs after some time, so RocksDB has this compaction algorithm, this automatic compactions, and we implemented compaction hooks that do some specific cleanup during compactions. So for example, old values that have been overwritten are being discarded during this compaction, provided that they're outside of this history retention window for which we want to be able to read data as of a particular time in the past. As for example, during transactions, it's useful to be able to read data as of the start time of the transaction. So the compaction does the cleanup, and it reduces the number of SS table files. And then just a slightly different example, we could have a compound key like K1 and K2 are components of the key, and this is also an extension to the SQL syntax. K1 is a hashed column, and K2 and K3 are ascending range columns, and we only hash the first column, and K2 and K3 are just included in the encoded form of the RocksDB key. So then there is a similar value.
Awesome. So few questions coming up, Mikhail. So maybe one or two, let me just like ask for the sake of clarity. I thought I saw a question, but it went away maybe from Mikhail. But anyways, so the hash syntax, right, especially in YSQL, which is Postgres compatible, that is something that we have introduced, right?
Yes, that's an extension.
Right. And if you said hash, then the subdoc key would have the hash piece, which is the 0x7fc1, which is kind of the distribution value that goes into a random tablet. And if you said ascending or descending, then it wouldn't have that piece. Is that right?
Well, technically, it's not subdoc key. It's kind of this.
No, I meant like the place at the bottom. Yeah,
yes.
The place where it says subdoc key. That yeah, but I do.
Right.
Yeah.
Yes, but so there are these hash columns and there are these range columns, and the hash value here is calculated based on this sequence of hash columns. So there could be more than one hash column. So this is a very useful extension of SQL for distributed databases.
Yeah. So this is added into YugabyteDB by us. It's not really something that exists elsewhere, and this is just a very nifty way to control distribution strategy of data, right? Like, so that is one question, right? The second piece that I just wanted to point out is the HT physical : that big number. That is really the hybrid logical clock, right? Across the cluster that's what that represents. So we are able to kind of figure out at what time changes happen across different nodes or different tablets living on different nodes, because this is the value for one particular row or column in one node, right?
Yes. So this is based on the microsecond timestamp, and there could be a logical component here if the writes are happening quickly enough so that the microsecond timestamp doesn't change. We would increment a logical component, and this hybrid logical clock also works by propagating the value of the clock across different servers. So for any sequence of causally connected events, such as connected by RPC exchanges or events happening sequentially on one node, the logical timestamp, or actually the overall tuple of physical timestamp and logical timestamp, will be lexicographically increasing. So that helps with transactions.
So Kishi Kumar asks, how do you make sure the new key generated from the modification resides next to the original modified key? I guess it's in the previous slide is the question.
So yes, so all of this is they're encoded in a way that has a very specific sorting order in the RocksDB. So for example, here, so for each key, if the keys are only different in the timestamp, we sort them in the decreasing order of the timestamp. So for example, here we see 2.7 and 2.2, and this timestamp is larger, but then this timestamp is smaller, and this is sorted first. So the newest value of the row is sorted first. But when we have per column overrides, all of those are, so all of these three values here that don't have a column ID, they are replacing the entire row, because this is inserting the row, this is deleting the old value of the row, and this is inserting the older version of the row. But this override, we add the column ID, and all of these are stored after, or sorted after this full column override section, and that's purely based on how the encoded values are sorted in RocksDB.
So I think a bunch of stuff. So just hurrying on. So Colt actually, hey Colt, asking a question on what compaction strategy is used by default with YugabyteDB. I think you do have a section on this, so maybe it's right after this section, I believe. So maybe we can just like breeze through this section and go there.
Yeah, we can actually maybe talk about compactions first, and then if we have time to come back to some other improvements. So we use the universal compaction strategy in RocksDB. The universal compaction strategy is let's say it looks at this space amplification. So it starts from the newest files, which are typically the smallest files, and we aggregate the sizes of files, and then the size of the ratio of the next file compared or divided by the aggregated sum of sizes of smaller files needs to meet a particular ratio, at least a particular configured ratio. So in this example is 1.2, and that's when we decide where to stop aggregating the files, and we use those files as the input for the compaction, and we replace those files as replace them with a larger stable file that is generated by merging them. And sometimes the file might actually be smaller because there might be deletes, and we discard some old outdated data. So we end up with a smaller set of files. And so this is
the compaction strategy. I think we call it universal compactions, right?
Yes, it's called universal compactions in the RocksDB, and we only use one level. So RocksDB came from LevelDB, and LevelDB had a different compaction strategy, level compaction strategy, but we put all the files into one level.
Yeah, and I think the rationale there, I think for Colt is LevelDB was I think more of a browser side storage database, so it had to look at space amplification, whereas RocksDB and YugabyteDB are more traditional transactional databases, and they have to look at IOPS, right, more than storage space, right? Like is the intuition, and the fact that it's sharded into multiple tablets, that also helps reduce the space amplification. Is that right, Mikhail, roughly?
Yes, so they have different space amplification trade-offs. And so what the leveled compaction strategy allows one to do is there is a strict limit on the number of files that you would have to read, because each level is partitioned by a range, and you would only have to look at one specific file in each level. So we don't do that. Instead, we make it more. We use the same strategy that we used in HBase that worked well for us in server-side workloads.
Makes sense. Yeah. Let's keep going. So what did we do? What all of the enhancements we did for compactions? So yeah.
So for compaction specifically, one of the big enhancements was priority thread pool. So we prioritize different operations that run in the same set of thread pools. So large compactions and small compactions are, I guess, they're divided by size, but sometimes we do full compactions in case we aggregate all the files and decide that it's time to combine them into one file. Those are called major compactions, but still we divide them by size into small compactions and large compactions. And sometimes when you accumulate too many files in a particular RocksDB instance of a particular tablet, RocksDB would stop writes until the number of files decreases. So that's undesirable, because that's a loss of availability for writes. And we prioritize, so we prioritize flushes first, but then we prioritize compactions where we don't allow writes, or where we have stopped writes altogether. Then the compactions where the writes are delayed or throttled because the number of files is approaching the maximum value. And then other small compactions are the next highest priority, and then large compactions that could just run in the background for a while are the lowest priority. This also even allows us to pause a particular compaction while if a higher priority operation shows up, like a flush or a small compaction. And another improvement that we did is support for TTL file deletion, and sometimes, that's specific to Cassandra query language compatible, YSQL compatible workloads. So there is TTL. So for time series data, for example, a workload could retain only a specific amount of data or a specific amount of time, and data that is older than that should be discarded. And to do that more efficiently, we don't compact the files that are that are over a certain size, and instead we wait for those files to become old enough so that they could just be deleted, because we know that all the data in those files has expired. So and then there are other optimizations, like, for example, for compaction specifically, like scheduled compactions, scheduled full compactions that could be run during off-peak times. Compactions that are also triggered by, there was a separate talk on that, compactions that are triggered by, let's say we accumulate a number of deletes and we are spending a lot of time going through those deletes, then the system automatically finds that situation and it schedules a compaction. But I guess maybe what we should do is go through these other,
some of the core enhancements. I think
yes.
have another 2-3 minutes. So
yeah, so the core enhancements to RocksDB that we did are, for example, server global block cache. So we don't use per RocksDB instance block caches. We just combine all of them into a larger block cache, and it is controlled by these flags. It is set automatically on the amount of memory, but sometimes for some workloads it needs to be adjusted, and we're constantly trying to make the system more automatic and set these parameters automatically. And we currently don't size the block cache size dynamically. We don't set it dynamically based on other memory needs of the system, but that's probably one of the directions that we will explore. And then another cache improvement is scan resistant block cache. So for example, if you scan a large table that is larger than the size of your cache, you don't want all the data from the cache to be evicted. So to support this, we created this single touch versus multi-touch cache system, where the single touch cache is the blocks that have only been read once, and it is limited to, let's say, 20% of the cache by default. And if there is enough memory in the overall cache, it might take much. It might take more than that. But as soon as you read a particular block cache or access a particular block or block in the cache more than once, it goes to the multi-touch section, which is allocated 80% of space by default. So what happens in a scan is that you will only touch those blocks once, and they will compete for space in the single touch portion, and they will not evict 80% of your warmed up cache. And then another big enhancement, it's similar to some of the work that we did in HBase. RocksDB has, as a stable format, has Bloom filters to quickly decide whether a particular file contains a particular key, and those Bloom filters can grow large. And similarly, it has block indexes that allow to navigate to a particular key in the stable file, and those indexes can grow large. So there is a need to split them in smaller blocks, and those blocks also have a small index on top of them, and those blocks can be brought in the cache independently. So we don't have to read the entire Bloom filter or the entire block index of the SST file. And this is a little bit of the format. So currently we split the metadata into one file, and the data is in one more file, and it's just one file for now. So a future extension might be to support multiple files for storing the actual data, but right now it's just one file, and it has this format that we talked about, which with separate blocks for or separate sets of blocks for Bloom filters and for block indexes. And some of the other improvements are, so our system is aware of multiple disks, and for example, it's gonna try to free up the disk that has the lowest free space when deciding what tablet to remove from a node in case, for example, if we're scaling out the cluster and we need to rebalance the load. And then we briefly touched on this point as well. So only the Raft committed records are ever applied to RocksDB, but RocksDB is flushed independently, and when we restart the server, we need to decide what part of those records to replay. And we do that by looking at this new bit of RocksDB metadata that we call frontier, which says what is the maximum op ID of Yugabyte raft operation that has been flushed into this file. That's how we avoid using the RocksDB write-ahead log, and we just completely turn it off. And of course, and I also briefly mentioned this, that we have, for transactions, we have actually two RocksDB instances. We call that regular RocksDB and intense RocksDB, and intense are just records of uncommitted transactions and also some logging information. And we have separate metadata. So the server restart workflow is actually quite complex. It has to look at multiple types of metadata and decide what types of records to replay and what types of records to skip, and also which parts of the write-ahead log even need to be read, because when you're restarting a server with a lot of data, with a lot of tablets, that could be time-consuming. And yeah, I guess maybe the last improvement I should mention here is the global per server mem table. RocksDB out of the box flushes files when they reach a particular size, but we don't have to do that when we run multiple RocksDB instances per server. So instead, we have a global mem table size, and when that is reached, a global mem table size limit is reached, we find the oldest mem table and we flush that oldest mem table.
Awesome. Maybe we will pause there to see if there are questions. I think we're a few minutes over. So I think there's been a lot of good questions, a lot of good interactions. So that's amazing. Thank you, guys. Should we do perhaps a follow-up on this, given the interest? Mikhail, what do you think?
Yes. So
topics still left here. So
yes. So we need, I guess, based on the questions, but we haven't touched on the transactional part of the storage subsystem. What else? I mean, there are a lot of good topics. So based on what the questions are about, I think we can decide to focus on maybe an adjacent but a slightly different
aspect
around RocksDB for the next part.
All right, let's do that. Okay, thanks everybody. I think Kurt says great talk. So yeah, thank you, Kurt. Hope you're doing well. All right, so that brings us to the end of the talk, folks. Thanks a lot. Really appreciate all the effort into putting this together. Mikhail has been amazing, really informative, I think, and as the interaction has been great, interest looks great. So thank you, everybody. See you again in a couple of weeks, same place, same time with another topic. But until then, thanks. If you have questions, feel free to ask us on LinkedIn or drop it into join our community Slack and ask us in the YFTT channel. Venkata says thanks. Yeah, thank you, Venkata. So yeah, I think thanks a lot, folks.
Thanks, everyone. Thank you, Karthik.
Absolutely.